Hi folks, Mr. Long here. We're going to work today on a screencast on how to rough sketch composite function graphs or square root function graphs. And this is, it's very much like the work that you did in advanced functions. It's just recognizing that there are different types of x-intercepts. So for example, let's go through and see if we can recognize some of these. Based on the work that you did earlier, hopefully you recognize that as a one-sided cusp. A one-sided cusp is vertical tangent where it touches, but you can see that it only, in this case, it only goes to the right. And what would that look like? Well, something like t exponent 1/2 or 1/4, 1/6, something like that. So an even exponent on the, so it's odd over even. Like 3/8 would look the same way, right? So square root function, as an example, 1/2. Then you can have what's called a saddle point, where the slope is 0, so it's a horizontal tangent, but there's no turning point. So it decreases, goes horizontal, and then decreases again. That's something like a cubic, right? That's something like a cubic function. So we have cubic functions there. A cubic function is a saddle point. A local max or min, right on the x-intercept, which is, we're quite familiar with that. That's a degree 2 or a quadratic or a double x-intercept, we call that. Okay, so local max, and then a two-sided cusp. What it does, it has a vertical tangent right there, and then it reverses and comes down, or goes up. And so it can actually be a minimum or a maximum. It will have a form of even over odd. So 4/5 would also work, 2/3, anything. And again, we went through the mathematics of that earlier with calculus to understand that. So that is what's called a two-sided cusp. Again, vertical tangent. Then you have the nice smooth vertical tangent here. So this has a vertical tangent. This has a vertical tangent. This has a vertical tangent as well, but it's nice and smooth, right? So it passes through. So this is, for example, a cube root, okay? So it's a odd over odd, like 1/5, 1/7, 3/7 would all look the same way, okay? So, and again, it just continues on. So those are examples of types of x-intercepts. So it's no different than, again, what you did in advanced functions when you graphed polynomial functions. Now we're graphing factors that have fractional exponents instead of whole number exponents. A couple things I want to address with you, that just to make sure you understand this, is what's the difference between this and this? Okay, what's the difference between those two, x minus 9 squared versus x squared minus 9? Well, x minus 9 squared is a repeated root of x minus, like a repeated factor of x minus 9. So to solve that, we square root one side, we square root the other side, and x minus 9 equals 0. This is a double root because the square is being applied to the entire factor. Okay, the entire factor. So that's one double root of x equals 9. Over here, though, it's x squared minus 9. So in fact, the squaring is only applied to the x. And I could have factored this out and had x minus 3, x plus 3. So I get x squared equals 9, or x is plus and minus 3. This is two single x-intercepts, or linear, right? So a single. And I don't think I showed a single on that picture, did I? So a single x-intercept, what it would look like is this. So maybe it comes down here, but it crosses there, like so. So it looks like a line as it crosses the x-axis. Okay, but it won't be straight up. It's not vertical. It can't be vertical. And it could be also very, very shallow too. Like it can be not very steep, or it can be quite steep. It just can't be vertical. Okay, so that's a double, and that's two singles. Now, how does that relate to the fractional ones? Well, let's look at the fractional ones. So what we have here is x minus 5 to the 1/2. So what does that look like, right? What does that look like? X minus 5 to the 1/2 is x equals 5, because that's what makes it 0, and that's a one-sided cusp. So what would that look like? Well, it would be at 5, and then it would be vertical, and then curve like a square root graph does. Okay, but it's a vertical tangent right here. So then I go over to this equation, x to the 1/2 minus 5, right? So this might be a factor in an equation. And again, the 1/2 is not applied to the entire factor. The 1/2 is applied only to the x. So you can see the inverse operations. We let x to the 1/2 be 5, then we square both sides to get rid of the 1/2, and x equals 25. That's just like x squared minus 9. Okay, that's just like working with x squared minus 9. That's just a single. So that would be, you know, out here at 25, and maybe the curve comes across like so. It's a single x-intercept, okay, because the x is not, or the exponent of 1/2 is not applied to the entire factor. Okay, so you'll need to know that as we work through these questions. So let's start graphing. So here's our first one that we're going to graph. And I'll be zooming in and out on these just so you see them. So this is, you have a sheet of like, there's like 15 questions. Again, do you need to do all of them? No, but you should probably sketch as many as you can. And I've got this, this structure here. You can print these out if you want. But I just did it as an organizer. If you want to use it, you don't have to. So what we're going to do is we're going to do rough sketches by getting x-intercepts and n-behavior, just like we did in advanced functions. So here's the first one that I want to sketch. Okay, and we're going to add on calculus later. But for now, we want to go ahead and get a rough sketch, make a rough sketch of this. Okay, so one of the things you're going to want to do is to check the end behavior. Well, what would the end behavior on this one be? The end behavior is related to the leading coefficient, and the leading term is the highest exponent. Okay, and it shows the behavior left and right, far to the left and the right. So if we look inside the bracket, so in the composition, we look at x squared, that's the biggest exponent, but the x squared has a 2/3 applied to it. So let's go over to here, okay, leading term. So I have a 3, it's a positive 3, so I don't even really need to leave it there. Then I have x squared to the 2/3. That's my leading term. Now I need to multiply the exponents together. In this case, 2 times 2 is 4/3. So how does that affect the end behavior? So I want you to think about that. What does that mean? Well, the 3 means cube root, the 4 means exponent 4. So if, for example, I had a negative for x, I would do the cube root first. I wouldn't have to, but I could do the cube root first, and the answer to that would still be negative, but then I'd raise it to the exponent of 4, which would remove the negative and turn the negative into a positive. So when we think about this, no matter what I put in here, unless it's 0, but if I put a negative number in here for x, because of that 4, the result's always going to be a positive. So it's always going to be 3 multiplied by a positive. And I can even think of it as the x squared to the 2/3. The x squared is automatically going to turn out to be positive, and then after that, it's just raise it to 2/3. So that's probably even a better way to think about it. The x squared is always positive, and then you raise the exponent 2/3, it's still going to be positive. So far to the left, it's going to be 3 multiplied by a positive, even though x is negative. That's a positive. So far to the left, it's up high. Remember, we're referring to the y value here. So as x approaches negative infinity, y approaches a positive number. What about far to the right? Well, again, 3 multiplied by a positive, because x squared is positive. So, and then you apply the exponent 2/3, it's still going to be positive. So our far to the left, our y value is up high, and far to the right, our y value is up high. Now, what about x-intercepts? X-intercepts require some factoring. So I thought I would go through this example and factor it with you so you can see it. So I've got this equation here, and what I always want to do is factor the inside where possible if there's factoring that needs to be done in the inside of the function. So I've got 3, and then in brackets, oh, by the way, you want to factor it before you do the domain. I apologize, I didn't, that's what we're going to do now, is the domain. So I want to factor the x squared minus 2x. So to factor that is x, then in brackets, it would be x minus 2, right? And then it's to the 2/3. Okay, so can I continue with that? Can I continue to factor that again? Yeah, I can. Because that 2/3 applies to both the x and the x minus 2. So it would be x to the 2/3, and then x minus 2 to the 2/3. So when you're doing the domain of a product of functions, what you do is you check both factors, or 3 factors or 4 factors, and you look at the domain of each factor, and then the factor that is most restricted, the factors that are most restricted are the ones that will govern the domain. So if you look at this, and again, I always think about it as putting a negative in, putting 0 in, putting positive in. So can I put a negative in there and get the cube root? Yeah, for sure I can, because the cube root in the bottom, and then I square it. So I can have negatives, I can have 0, I can positives. So the domain for that is all x. What about the other factor? Well, can I put it's a cube root, so am I allowed to have negatives inside here? Yeah, because I can take the cube root rather of a negative. 2 over 3, the 3 is the cube root. So I can have a negative, I can have 0, I can have positive. So what's the domain for this graph? All x. Okay, so all x. So x belongs to the real numbers. Okay, x belongs to the real numbers. I can have anything I want for that. Okay, determining the actual x-intercept. So let's do that. So I've already did the factoring up above, so I'll just show you it right here once we've factored it. And so the first factor you're going to get out of there, the first x-intercept rather, is x equals 0. That's the solution to that. And then when we look at that, it's x to the 2/3. So x to the 2/3, that is a two-sided cusp. Okay, so we know what that looks like. It's a two-sided cusp. And then the next thing we're going to do to look at this is we're going to look at this factor here, x minus 2 to the 2/3. Well, obviously the x-intercept is 2, and because of the exponent of 2/3, it's a two-sided cusp as well. Okay, so both of our factors have two-sided cusps, for both of our x-intercepts. So, some things that, when I go to sketch it now, some things I need to think about. Well, I know that when I'm far to the left, it's up high. When I'm far to the right, it's still up high. So that's why I've put the green there and the green there. So that's where I would start. And then after that, I would go and look at my x-intercepts here and here. And in both cases, they are a two-sided cusp. But I know it's starting here, and I always read my graph left to right, so I come down, down, down. It has to open up rather than opening down, right? It's not going to open down like that, otherwise it doesn't fit the end behavior. So then it has to go up here, has to turn and go back, and then again, another two-sided cusp, and like so. Okay, so that's your graph. So that's just like graphing, x minus 3 squared times x plus 5 cubed, just like you did last semester. It's just now the x-intercepts look a little bit different, right? They can be cusps, and they could be odd roots as well. Okay, so that's what your graph looks like. And then you can imagine now with calculus, you've got a point there where there could be a maximum, and these points here could be local minimums. Okay, folks, here's another example that's very similar to sorry, I was just checking the recording was working properly. So it's very similar to number 9 on your handout. And so here's what we're going to do. This one is x multiplied with the square root of 2x minus 5. And if we're going to look at end behavior of this one, we've got, well, actually, before we do that, we should always do domain before we do end behavior. That's important because you're going to see a reason why we would do that. So the first thing we're going to look at is this x in the domain. Again, when we do the domain of a product, we look at each of the domain within each of the factors. Okay, so what's the domain associated with x? Well, what kind of numbers can I put there for x? Can I put negatives? Can I put 0? Can I put positives? I can put anything at all for that. So that x here belongs to the real numbers. That can be anything. As for the 2x minus 5, however, we see that that's a square root. It always has to be greater than 0 or equal to 0. So 2x minus 5 has to be greater than or equal to 0. So I would add 5 and divide by 2, and I know that x has to be greater than 5 over 2, which is 2.5. So I'm going to go down to the graph here and mark that 2.5 on. So I know that every single x I have that I'm allowed to have has to be greater than or equal to 5 over 2, 2.5. Well, am I allowed then to let x equal 1? No. Can I let x be 2? No, because then I would get a negative under the root sign. The smallest x I'm ever allowed to have is 5 over 2. So when we go through this, we go through each factor, and then the factor that is most restricted, or is the factor, or it could be more than one factor, but we look at the factors that restrict, and that's how we come up with our domain. Okay, so our domain in this case is right there. X has to be greater than or equal to 5 over 2. Now we can do the end behavior. Okay, now we can do the end behavior. And I think what I'm going to do is just so what is the end behavior for this one? So what is the leading term? Well, I've got an x multiplied by a root x. Okay, an x multiplied by a root x. So that is x to the 1.5, right? Because it's a half and 1. That makes 1.5. Now, do I have to worry about far to the left for the end behavior as x approaches negative infinity? No, because x has to be greater than or equal to 2.5. So there is no left end behavior. Now, what about far to the right? Well, for the end behavior, again, it's the leading term, the base with the largest exponent after you multiplied out the product. So, yeah, you multiplied out the product. So it would be, you've got an x here and a x to the 0.5 there. So it would be far to the right, it would be a positive all to the exponent of 1.5. Well, that's just going to be a positive. So I know the graph is way up high here. Let's look now at the x-intercepts. So it looks like x equals 0 is an x-intercept because of that first x. The x multiplied by root 2x minus 5. But it can't be because of the domain. X equals 0 doesn't exist in this graph. The only x values I'm allowed to have to be greater than or equal to 2.5, 5 over 2. So when I look at this, 5 over 2 is a valid x-intercept because that's what makes the part underneath the root sign 0. And I'm allowed to have 0 under a root sign. So I'm going to go down to here, and I've got these little charts to analyze the roots. So this one is, it's got a square root outside of it, therefore it is a odd over even root, and it's a one-sided cusp. So if I look at this, when I go to sketch it, so in terms of sequencing, what's the sequence here? First, do your domain. Second, do your end behavior. Third, do your x-intercepts, then sketch. So I've got a one-sided cusp. So do I want A, would I want my cusp be going, one-sided cusp be going down, or B, would it be going up? Which one works? Well, I'm pretty sure, given that the graph finishes up high because of the end behavior, I'm going to have to use the one that goes up. So it's going to go like so. So it's a vertical tangent there, and then it just goes like that. We don't know exactly what it looks like, but something like that, right? And it actually might be even a little steeper, but we just know it goes to the right. Okay, so that's a pretty good rough idea of what this graph would look like. Pretty simple looking graph actually, but again, you have to. It's tricky. Okay, folks, I'm going to stop there, and there's a few more to do, so I want to chunk this into 2 separate videos because this process is fairly lengthy going through this. So there's going to be another part 2 of this coming up.